Linear functions and relations. Graphing linear equations and direct variation. Now, the thing to understand about linear equations is that it's really just an equation that forms a line, and a line is just a point that continues infinitely in both directions. Now, there are two ways to express linear equations. You can do it in standard form or slope-intercept form. Standard form is written as ax plus by equals c, and slope-intercept form is y equals mx plus b, where m is the slope and b is the y-intercept. Now, x and y can be any ordered pairs in the line. Slope. Now, slope is really just the vertical change over the horizontal change between 2 points, also known as rise over run. To find slope, you can either just look at the graph or use the equation y2 minus y1 over x2 minus x1.
Graphing linear equations and direct variation. Now let's try some problems. Put the following equation in slope-intercept form and graph it. As you can see, our equation is in standard form. We need to put it in slope-intercept form. What we're going to do is isolate the y all by itself on one side. Usually that's the left side. So, to isolate the y, we need to get rid of the negative 4x. To do this, we add 4x to both sides of the equation. When we do this, we get 6y equals positive 4x plus 12. Now, the y is by itself, but there's a 6 in front of it. So we need to divide both sides of the equation by 6. As you can see here, when we divide by 6, we get y equals 2 over 3 x plus 2. And that's, again, 4x divided by 6 and 12 divided by 6. This is our equation in slope-intercept form. Next, we're going to want to graph this equation. First, we want to plot the x and y intercepts by zeroing the x and y. To do this, we either make the x equal to 0 or the y equal to 0. First, we're going to make the x equal to 0. When we zero out the x, we get 2/3 times 0 plus 2 equals y. 2/3 times 0 is 0, plus 2 is 2, so our y-intercept is 2. It's also written here, b is the y-intercept. So we plot our y-intercept at 2. Plot any additional points as necessary. It's not necessary for this graph, but sometimes if you plug in other x values, such as -1 for instance, you will get another y value that you can plot a point here. To plot the x-intercept real quick, we need to make the y 0. So if you make y equals 0, 0 equals 2/3 x plus 2, and when we plug that into equation, our x equals -3. So as we see, we plot that here, -3. Finally, you connect your dots with a line, straight line with arrows on either end. Graphing linear and direct variation equations continue. As mentioned before, slope is rise over run, and the formula for that is y2 minus y1 over x2 minus x1. Let's look at problem 2. Find the slope of the line that passes through the points -2, 3, and 4, 6. When I'm doing this kind of equation, I like to label my x and y values. So as you can see, I've done that here. This is x1, y1, x2, and y2. Now that they're labeled, it makes it easier to plug it into the equation. As you can see, I've done that here. y2, y1, x2, x1. Next, all we have to do is simplify that out. 6 minus 3 is 3. 4 minus the -2, which is also a 4 plus 2, is 6. 3 divided by 6 is 1/2. That's our solution. Problem 3. Graph the direct variation equation, y equals 5x. Now, before we graph that real quick, let's take a better look at what direct variation is. The direct variation equation is y equals kx. As you can see, there is no y-intercept, and that would be the b. As you can see, it's not there. K is the constant of variation. Before the x, it's also known as the slope. Back to our equation. Y equals 5x. 5 is the slope, and there is no y-intercept. First, we're going to want to make a table of values. I've done that here. For our table of values, I've picked the points -1, 0, and 1. These points are good starting points for any graph. It doesn't have to be direct variation. Next, we want to plug these x values into our equation. So, if we plug in -1, 5 times -1 is -5. Y equals -5. For 0, 0 times 5 is 0. y equals 0. And finally, for 1, 5 times 1 is 5, y equals 5. Next, we want to plot our points here. So -1, 5, 0, 0, and 1, 5, as I've done. Next, draw a line connecting the points and put arrows on either end. As you can see, this graph passes through the point 0, 0. All direct variation equations will pass through the point 0, 0 because there is no y-intercept.
Now let's learn how to solve one-variable equations. So the essential understanding here is that a solution is any value that can replace the variable making the equation true. You can solve equations by graphing or by using algebraic properties. So what we're going to do here is graph them. Problem 1. Solve 5x plus 2 equals 27. The first thing we have to do is isolate the variable. We're going to do this by bringing the 2 to the side so the variable is all by itself. Then we're going to simplify it so the variable is actually by itself and doesn't have a coefficient. That gives us x equals 5. So that's our solution here. If we plug in 5 for x in the original equation, both sides will equal 2, and that means that it's equal. So it's right. Problem 2. Solve the absolute value of 13x minus 2 times 3x plus 1 equals 8. The first step here is using the distributive property to get rid of the parentheses. So that gives us 13x minus 6 minus 2, the absolute value, equals 8. So now you have to combine the like terms, so we get the absolute value of 7x minus 2 equals 8. Now we want to get rid of the absolute value by putting it on the other side. The way we're going to do that is just transfer it over, and then the absolute value of 8 is either plus or minus 8. We know that. So now we have two parts. We have if it's plus 8 or if it's minus 8. That means over here we have 7x equals 10 over 7. 7x equals negative 6 over 7. So we're just simplifying the 7 out, so it's really x equals 10 over 7 or x equals negative 6 over 7. Now let's solve two variable equations. There's two methods to do this. We can do it graphically or algebraically. Here we're going to do it graphically. The equation we're trying to solve is y equals 1/2 x plus 1/2. So basically what you have to do here is you just have to graph the line. Here's our line graphed, and here's a bunch of points on the line. All of these points are solutions because they fall on the lines. But here's how you do it algebraically. Now we're solving for y in terms of x. This means we pick a value for x and solve for y. The problem we're going to use here is 2y equals 4x plus 4. We want to simplify down a little bit so it's easier to work with. So we're going to divide both sides by the 2, giving us y equals 2x plus 2. So now we're going to choose an x value and plug it in. The x value we chose here was y, x equals 2. So now we're going to plug it in over here. Y equals 2 times 2 plus 2. That simplifies down to y equals 6 because it's y equals 4 plus 2. So 2, 6 is our solution.
Next, we're going to talk about how you solve and graph linear inequalities instead of equations. And typically, you want to do the exact same thing with a few differences. For example, when you solve, you want to solve in the exact same way that you solve an equation, except when you multiply or divide by a negative, you want to switch the sign. So if you have greater than, you want to switch it to less than. And if you have greater than or equal to, you want to switch it to less than or equal to, and vice versa. For graphing, you also want to do pretty much the same thing. The line, in fact, is the exact same thing, except the fact that when it's greater than or less than, it's dotted, and when it is greater than or equal to, or less than or equal to, it's solid, like this. When you graph an inequality, you also have to shade either the top or the bottom. And so that you know whether you want to shade the top or the bottom, you pick a point that's not on the line here. And say we pick 0, 2. You then plug it into the equation, and if it makes the equation true, then it's a solution, and you shade that side. Now a bit of review. I want you to put this equation right here in slope-intercept form. Then, when you're done with that, I want you to find a solution algebraically. Then, when you finish that, I want you to graph the inequality, right? So just graph it. And when you're done with that, find a solution of that inequality using the graph. So here are the answers to the first and second one. The third and fourth are a bit hard to write on paper without making it super obvious. But if you put this in a mirror and you flip it upside down, then you'll see the answer.